Hi, so in this video, we're going to do some examples, and I thought we would start with 4 different ways to construct a mod-10 counter. So I've listed all 4 ways, but let's just tackle them one at a time. So the first way I want to do it is written here in A. Synchronous up counter with asynchronous reset using JK flip-flops. What does this mean? So if you cast your mind back to when we constructed our asynchronous up counter with asynchronous reset. So to be clear, we used the asynchronous reset method when we had non-natural mod numbers. So in other words, mod numbers that weren't powers of 2. So we did a mod-9 up counter, and there are 2 videos. And in one of the videos, we did it asynchronously, and in the other video, we did it fully synchronously. And what I'm asking here in A is a kind of hybrid of the 2, where you have this fully synchronous mod 16 up counter. So if you recall back when we did the asynchronous mod 9 up counter, what we actually did was build an asynchronous mod 16 ripple up counter, which we know how to do. And then we did this kind of, we performed these hijinks where we asynchronously reset the counter back to 0 when we reached the first invalid state. And that's the technique that I'm asking for here in A.
Recall that our strategy when we were doing this asynchronously, our strategy was to build the mod 16 up counter, right? And just perform that asynchronous reset. And that's what we're doing here, except that our mod 16 counter is going to be fully synchronous. All right, so recall that generally for a fully synchronous counter, I wire pre and clear, or anyway, those asynchronous inputs, I will always wire them to be inactive. So if they're active low, I'm going to wire them high. So normally I would write pre equals clear equals high, but I'm not going to do that. Why? Because I need clear to be connected to my reset circuitry. So just pre is going to be wired high, and I'm not going to show it on my schematic just to make things neat. Now, the second thing is, recall this is still a synchronous mod 16, right? So I still have a clock. Let's make them negative edge triggered. Now again, it does not matter for a synchronous counter. So I will connect the clock here and here. So again, this differs from an asynchronous counter in that it's the same signal that's wired to the clock inputs of every flip-flop. All right, and next thing. So I'm not going to go over the excitation table for a mod 16 up counter, but you will recall there is a pattern, or I hope you recall, there is a pattern. So the pattern, and this only applies to natural mod number counters, synchronous counters. So the pattern is that in the first flip-flop, the least significant bit, J and K are both wired high. And in fact, for all the flip-flops, you'll notice the J's and the K's are wired together. Now, for J1 and K1, they are wired to Q0. And J2 and K2 are wired to the ANDed inputs of Q0 and Q1. While J3 and K3 are wired to the ANDed inputs of all the 3 previous stages. That is Q2, Q1, and Q0. So I could have done a 3-input AND gate, but instead I did 2 cascading 2-input AND gates, and they are equivalent. And my counter outputs are simply the Q output, so not the Q bar output. So in a synchronous counter, it's always the Q outputs. Now, if you are in doubt, maybe you're wondering, what did I just do? How did I know to do this? The reason I knew to do this is because I have previously done the excitation table. So not in this video, but it was done in another video. And when you do the excitation table for a fully synchronous natural number mod counter, you get this kind of pattern. And in fact, if I had wanted to do a mod 32 up counter, I would have added another flip-flop, so somewhat to the left of J3 of Q3, sorry. So it would have been the output of it would have been Q4, and the J4 and K4 would also have been wired together, and they would have been the ANDed inputs of all the 4 previous stages, so Q0, Q1, Q2, and Q3. So that is a pattern. But I am assuming now that you have watched the previous videos or you have tried your hand at it and you know this pattern, so I have not gone over it. So step 1 complete. We've built a fully synchronous mod 16 up counter. Now for step 2. What is step 2? So step 2 is build the asynchronous reset circuitry. So over here, I'm just going to draw sort of a little box around it. Okay, this is my mod 16 fully synchronous up counter. And now what I'm going to do is I want to reset it at state 1010, which corresponds to 10. So what is going to happen is that my synchronous counter is going to count all the way up from 0 to 9 at the next clock edge. So the negative clock edge. Why negative clock edge? Because I am using negative edge triggered flip-flops here. The next negative clock edge, when it hits the state 1010, it is going to reset. And how does that work? So 10 in decimal is equal to 1010 in binary, which has a nice kind of symmetry about it. So the bits that are high are Q3 and Q1. So as soon as these guys go high, I would like to reset the counter. So here's what I'm going to do. So this is my preset. And remember that preset is wired to VCC, but I have not shown it. I've just indicated it over here. As it just gets messy if I show it wired to VCC, but I might do that just for the sake of consistency. So let's wire them to VCC. Why not? Okay, what about clear? Also active low. That's what this little bubble means. So let's do our reset circuitry. The inputs to the NAND gate, and recall that the reset circuitry in an asynchronous reset circuit is just simply consists of an AND gate, and the inputs to the AND gate are simply the bits that are high in the first invalid state. So here it would be Q3 and Q1, and the output of the NAND gate is to all the clear inputs of all the flip-flops. The inputs are Q3 and Q1. And there you have it. So what kind of waveform is this thing going to give off? And it might be worth it just kind of sketch it quickly. So I want you to see that this is indeed a hybrid. So the timing diagram is going to look like this. All right, so what I want you to notice about this timing diagram is if you look at the features of this counter, you'll notice that it really is a hybrid because unlike a ripple counter, so here, let's look over at this clock transition. So this is quite interesting because at this clock transition, all the Q outputs are toggling. And if you look, you'll notice that they're all toggling at the same time. Now, I drew it out, but if you were to build this, let's say on a breadboard and scope it, you would see the exact same effect. All the Q outputs, they're all switching at exactly the same time. You would not have this, right? Recall that you would not have this in a ripple counter. In a ripple counter, the Q outputs they toggle in a staggered fashion. So Q1 somewhat after Q0, and then Q2 somewhat after Q1, and Q3 somewhat after Q2. And of course, the delay is just given by the TPD or propagation delay of the gate, the specific JK flip-flop that you're using. Now, what I do have, a feature that I do have that distinguishes this as not being fully synchronous are basically these weird glitches over here. So this you probably wouldn't even really notice on the scope. It would just look like I've kind of exaggerated the effect over here, but on a scope you would not necessarily notice that anything was amiss here at Q3. But you would definitely notice, if you zoomed in enough, you would definitely notice that at Q1 it kind of goes high momentarily and then it goes back low. So this here, this is a glitch. And this is a glitch that is caused by the asynchronous reset. And I can really see that when I look at this NAND gate. So the output of this NAND gate is consistently high. Now recall that this NAND gate is feeding the asynchronous, active low, clear inputs of all the gates. So it is high, meaning the asynchronous clear inputs are inactive until I get to this condition where Q3 and Q1 are both high. And that's the condition for triggering my NAND gate to go momentarily low, which is what happens here. When my NAND gate goes momentarily low, it issues a clear to all the flip-flops. So all the flip-flops go low, so they all clear to 0, and then the NAND gate goes high again, because the condition for it to be low is no longer in effect. Like the condition for it to be low was Q3 and Q1 being high, and that's no longer the case anymore because now they're all 0. All counter outputs are 0 now. So it effectively reset the counter. So I really get, when I look at the waveform, I really, and this is why I thought this was very interesting to look at, because I really get to see what parts of the timing diagram are synchronous and what parts are asynchronous. It's sort of like an interesting hybrid of the two strategies. And I just wanted you to see. So although I have this really nice, they're all toggling at the same time, all Q outputs are toggling synchronously, right? And synchronously with the clock. However, I do get this weird glitch, and that's caused by this, relic, this sort of like leftover asynchronous uh, part of my circuitry. And you know what, for the sake of thoroughness, let's just do the state transition diagram. So I kind of skipped over a lot of steps in this whole procedure. Like I didn't show you the excitation table, but if you were to do the excitation table, note that even though we're constructing a mod 10 counter, you would be doing the excitation table for a mod 16 up counter because we have that asynchronous reset to take care of transforming this mod 16 into a mod 10. All right, so how does this work? Now recall that for a mod 10 counter, from states 0 to 9, I am just going to unconditionally transition to the next state, which is the next state higher up in the sequence at the clock edge. So all the way up until 9, this is what happens. Now, when I get to state 9, for sure, recall the construction of my circuit, right? I am just going to unconditionally transition again to state 10. So also recall the timing diagram. When I get to that state 10, that's where that NAND gate kicks in. When that NAND gate kicks in, I have this asynchronous transition to state 0. Why? Because my Q3 and Q1 are both high. That's the condition for my NAND gate to go low, which issues the asynchronous reset. And what happens in all the other states? So first of all, before I move forward, I just want to note that here I have used this dashed or dotted line to represent an asynchronous transition. I don't have this. I would not have this in a fully synchronous mod 10 up counter. Now, what happens if I should, happen to power on my flip-flops and find myself in this state 11? What happens? Well, are Q3 and Q1 both high in this state? And in fact, yes, they are. Q3 and Q1 are both high. That's going to kick in that NAND gate action again. So it's going to reset asynchronously, reset me back to 0. What about in the next state? What happens here? So this is in state 12. In state 12, well, nothing really. I mean, if I power on in state 12, then I'm just going to unconditionally transition at the next clock edge to my next state, which is 13. Why do I do that? Because I have all that synchronous mod 16 circuitry. The NAND gate, recall, is inactive in this state because I don't have Q3 and Q1 both high. That condition is not true. So what about here in state 13? Well, I don't have the NAND gate kicking in, so I'm just going to behave as a normal mod 16 up counter until I get here to state 14. And what happens at state 14? Well, I do have that condition. Q3 and Q1 both high. So I'm going to make it a little neater. I'm going to go around 15 here. And again, this dash line is an asynchronous reset. That happens when the NAND gate kicks in. So what about here? In state 15, I've got Q3 and Q1 both high. Well, that's going to give me a little NAND gate action, and I am going to asynchronously reset to 0. Now notice this dashed line here tells me it's an asynchronous reset. If it was a synchronous reset, well, I mean, in any case, even if the NAND gate didn't kick in at this point, right, at the next clock edge, I still would reset back to 0 simply because that's the construction of my mod 16 counter. But I do have the NAND gate, the condition for the NAND gate to go low is true here because of Q3 and Q1. So this is the state transition diagram for my sort of hybrid mod 10 up counter. Okay, what's the next thing that I'm going to look at? Let's do B. So we've done A. I'm going to do B. So B is a fully synchronous mod-10 up counter, but it's using D flip-flops and don't care conditions for invalid next states. And I'm asked here to verify that all my invalid states have a valid path back to the counting sequence. So let's do it. So for part A, I took some shortcuts. I didn't do the excitation table, but for this, I do need to do the excitation table. So I'm going to start with that. Now you may be wondering, well, what about the state transition diagram? Aren't I supposed to do that first? And yes, you were right. You are supposed to do that first, but I'm going to get to that at the end. So up until state 8 over here, at state 8, I know that at the next clock edge, my next state should be 9. What happens at state 9? After state 9, I want to reset back to 0. Let's put that in. What happens in all these other states? Well, I have said up here, I said, you know what? For invalid next states, I'm just going to say that I don't care. I do not care. So what does that mean? It means that I'm going to put a big fat X over here. I could have written out each individual X in each individual cell, but I didn't want to because I was too lazy. What about the control inputs? So for D flip-flops, actually, you will see that it's the excitation table actually is really, really trivial. What does get more complicated is my Boolean logic expressions for my control inputs. So I only have 4 Boolean logic expressions because I only have 4 control inputs. If I was using JK flip-flops, I would have 8 control inputs. That's going to be the next example. But in this case, I only have 4 control inputs, but with one hand I give and with the other hand I take away. So it really is a trade-off. I'm actually going to end up having more complex expressions. For a D flip-flop, when I do the excitation table, I know that actually whatever I want the next state to be, that's what D has to be. So if I want the Q output at the next clock edge to be 0, well, that's really simple. D has to be 0. And if I want it to be 1, D has to be 1. And that's it. It doesn't get more complex than that. So really, the control input columns just mimic the next state for D flip-flops. Of course, for JKs, again, everything is much more complex when you're doing the excitation table using JK flip-flops, but I'm not using JK flip-flops. I'm using D flip-flops for this. And we'll contrast it. And my big fat X. And now I do my Boolean logic expressions. Again, this is the advantage of, even if I had a weird counting sequence, I highly recommend that when you write out your present state, you write it in sequence. So I'm actually just counting up. And I suggest you do this regardless because it makes your Boolean logic, your K-maps actually, makes them a lot simpler. Now, I want you to keep in mind what the purpose of these K-maps are. So the purpose of them is to express each control input, so D3, D2, D1, D0, in terms of the present state Qs. All right, now I've got all my Boolean expressions. So these are my simplified Boolean expressions in sum of products form. And I do need to do one other thing. So the thing that I need to do is I need to see what happens in my invalid state. So recall that I said I don't care what happens in the invalid states, but in actual fact, I might very well care. What happens if I happen to power on my counter and the flip-flops happen to land in one of those invalid states, so anywhere from 10 to 15. I just need to make sure I have a path back into the valid counting sequence. So in order to validate it, what I need are the Boolean expressions that I have. And I need to look at, so again, this is kind of like a reverse excitation table. This is kind of awkwardly worded. I called it validation for invalid next states, but I want you to understand what it is that I'm doing. What I'm doing is I want to make sure that for each of those invalid next states, that somehow they end up in a valid counting sequence. So not necessarily at the next transition, but maybe the transition after that or the transition after that. So what does it look like? So first thing I'm going to do is I'm going to look at all my invalid present states. I'm going to look at my control inputs. And I'm going to use those to determine what my next state is going to be. All right, so what I'm going to do here is, so usually I like to go one flip-flop at a time. So let's start with D3. So this, I've got this kind of monster expression for D3 here. I mean, that's not that bad, but definitely will be simpler for a JK flip-flop. I can almost guarantee you that. So I'm going to look, and I know that D3 is going to be high, or 1, logic 1, whenever I've got this condition of Q3 being high and Q0 being low, or if I have all three of these being high at the same time. So first thing I'm going to look at is, I don't know, let's just go term by term. So whenever Q3 is high, Q0 is low. So Q3 is always high. So where is Q0 low? It's low here and here and here. And so D3 is going to be high under those circumstances, but I also have to take into account this second product term. So it's also going to be high when all of Q2, Q1, and Q0 are high at the same time, and that only occurs down here. So I'm going to put a 1 there, and then all other circumstances, it's 0. Now I'm going to look at D2, and I do something similar for D2. So D2, the expression for when D2 is high is when either one of these three terms or any one of these three terms is high. So let's start with this, Q2, Q0 bar. So here's Q2. So when Q2 is high and Q0 bar is low, I'm going to have D2 being high. So that occurs here and here. Now let me look at the second term. So the second term is Q2 being high and Q1 being low. All right, so Q2 being high and Q1 is low in both these conditions. So I just need to add a 1 over here. And now my third term. So when Q2 is low, so that's these two rows over here, but Q1 and Q0 are both high. That only occurs over here. So let's put 1, and under all other circumstances, it's 0. What about D1? Same thing, D1. So I'm going to do term by term. I'm going to look at when Q3 is low and Q1 is low and Q0 is high. So Q3 low, Q1 low. Well, Q3 is never low. So this condition is never going to be true. What about here? Q1 and Q0. Is that a bar over the Q0? I think it is. So I'm looking for the condition where I have 1 and 0 here. So that's here and here, and that's it. So here and here. Okay, what about D0? D0 is high when Q0 is low, which is here, here, and here. But the next state for a D flip-flop is just going to be whatever D is, right? So whatever D is, that's what Q is going to be. So here, I'm just gonna write for the first row, the next state is gonna be 1, 0, 1, 1, 0, 1, 0, 0. I'm writing this out for the sake of thoroughness, but I mean, you can see that for a D flip-flop, actually, this becomes pretty easy. All right, what do I do with this information? So now I'm gonna do my state transition diagram. And if I had done this in the correct order, actually, I would just be revising my state transition diagram at this point because I would have already drawn it out. But again, because this isn't a complex state machine or anything like that, I took a little bit of a shortcut. But again, this is very much a case of do as I say and not as I do. Okay, so now I've got this, and I know, again, that from 0 all the way to 9, I count normally. What happens at state 9? I synchronously, at the next clock edge, so that's what synchronously means, the next clock edge, I'm unconditionally going to transition to 0. And I know this already, so this is the part that I should have done first, but I took a little shortcut. It's all the rest. So it's basically all these other invalid states. That's what I did here. So now this is what I have to look at. So what I'm looking at here, let's go state by state. I'm looking at state 10. What happens in state 10? My next state is going to be 11. All right, good. What happens in state 11? So this might be a little alarming because you might say, well, you know what? What happens if, I never get back into the valid counting sequence? But it doesn't have to happen in a single clock transition. This can take multiple clock transitions, but as long as it occurs, that's fine. So what happens in state 11? In state 11, I know that my next state is going to be 4. And that's promising already. So I'm just going to draw that arrow. And again, this is going to be a solid line indicating a synchronous transition. So if I happen to power on in state 11, I will go to state 4. And if I happen to power on in state 10, well, at the next clock transition, I'll transition to invalid state 11, but at the next transition after that, I'm going to go to state 4. Good. So what about here? What happens in state 12? State 12, next state is going to be state 13. Okay, well, don't get alarmed yet. What happens in state 13? State 13, next state is going to be state 4. Great. So far, this is looking pretty promising. Now, what happens in state 14? State 14 over here, 14 over here. The next state is going to be 15, but I'm not alarmed yet because I feel like something good is going to happen in state 15, which is that I end up in state 8 this time. So my final state transition diagram looks like this. And notice that regardless of which invalid state I end up in, if I happen to power on my flip-flops and they just happen to be in one of these invalid states, so regardless of which invalid state I end up with, I will always have a path back. Somehow, either at the next clock transition or the transition after that, I will somehow end back into the valid counting sequence. And once I'm in the valid counting sequence, I cannot get out. It's like Hotel California. You can check in anytime you like, but you can never leave. And that's what happens in the valid counting sequence. Okay, so this brings me to C. So we've done A, we've done B, and now what is C asking us? So it's asking us basically the same thing as B, which is what we just did, but instead of using D flip-flops, we're asked to use JK flip-flops. So I'm going to go through the exact same procedure, except that I'm going to use JK flip-flops. Let's get to it. Okay, so I've repurposed all my work from B, where I'm doing exactly the same thing but with D flip-flops. So I have repurposed it to now use JK flip-flops. What did I remove? I kept the excitation table. I was lazy, so I even kept the K-map. So what I removed was my control inputs. So my control inputs are the only thing that's different. The present state and next state, are the same. I even have the don't care conditions for invalid next states, so those have not changed. What has changed is that now my control inputs are J's and K's. Now I need to fill out my excitation table. So what I'm going to do is I am going to write the excitation table for a single JK flip-flop. So this is just for one JK flip-flop. I got my present state, next state, control inputs. Again, if you don't remember how to do this, go back to the first video in which we introduced synchronous circuits. I believe it was a synchronous mod-16 up counter. And take a look at how we derived this excitation table. So this did not come out of thin air. You absolutely are capable of remembering how to do it. You should not need to memorize this. I mean, if you do, that's great. And of course, like I always point out, there is this kind of mirror symmetry over here. But if you cannot remember, then just do the state transition diagram for a single JK flip-flop. And if you forget how to do that, go back to the mod-16 up counter video, and I promise you that this kind of these techniques, this kind of skill will serve you well in the future when we do more complex state machines. Okay, so back to our control inputs now. So what I'm looking at is I'm looking at the present state and next state. Of course, you will notice that it is more complex. It's 100% more complex to do an excitation table with JK flip-flops than it is with D flip-flops, 100%. But let's see if it pays off, because if I'm right, it should pay off with much more simplified control logic. So let's look here. Again, I look at present state, I look at next state, and I'm going to do it one flip-flop at a time. So right now I'm only looking at Q3. Control inputs are J3 and K3, and I look at the first row of the table. So I'm going to fill these out. Okay, I've gone ahead and filled out all the invalid states, and I'm just going to go over a few of them for you. So what I've done over here, I've written out all my invalid states. So that's anything outside the valid counting sequence. So this is the valid counting sequence. This is all the invalid states. And recall that when I drew up my excitation table, I said that I don't care what the next state was. But in fact, I actually do care. I want to know what the next state resolves to. And I want to make sure that if my flip-flops power onto one of these invalid states, they find their way back into the valid counting sequence. So what I did here was I wrote down all my invalid present states, and I looked for each of the control inputs. So let's start with J3. For J3, I looked at the Boolean expression, and I said J3 is only ever going to be high when Q2, Q1, and Q0 are all high. That only occurs down here. So J3 is only high here, 0 all the rest of the way. K3 is just Q0. That's this. What about J2? J2 is Q1 and Q0, and in fact, so is K2. So they're only high when both Q1 and Q0 are both high, which occurs here and nowhere else. And there's 0 everywhere else. What about J1 and K1? Well, J1 here is high when Q3 is low and Q0 is high, but Q3 is never low. So J1 is always going to be 0. What about K1? It's just Q0. What about J0 and K0? They're always high. Recall, that is the toggle condition for a JK flip-flop. So when I go to look at my next state, I look flip-flop by flip-flop. So now I'm going to go look at next state Q3. I see that present state Q3 is 1, and J3 and K3 are both 0. And I know that is the hold condition for a JK flip-flop. So I'm going to hold the 1. That's what I put here. What about over here? This is the reset condition. So I'm going to have a 0. What about over here? Hold condition, holding a 1. That's here. So you can see what I've done. I'm not going to go over all of them, but let's look at some of the more interesting ones. Here's a toggle. So J3 and K3 are in the toggle condition. I have a 1. I'm going to toggle it to a 0. And I basically just followed this logic the whole way through. So armed with this information, I now know what the next state is going to be for each one of these invalid states. So I'm going to fill out my state transition diagram. So in state 1010, next state is going to be 1011. So I'm going to draw that arrow. What happens in state 1011? Next state is going to be 8. Great. So here we go. I have a path back into the valid sequence. So now I look at this state, 12, and I see next state is 13. What happens in state 13? In state 13, next state is 8. So far, this is looking really similar to the D flip-flop. What about over here? This is state 14. Next state is going to be 15. But in state 15, next state after that is simply going to be 0. So I see that at every point here, I have a way back into the valid counting sequence. If I start off here, next clock edge, I go here, and then at the clock edge after that, I make my way into the valid counting sequence and just continue. Same thing here. I go here, make my way into the valid counting sequence, and if I end up here or here, at some point I will find myself back at 0, and I'll end up in the valid counting sequence. So all is good in the universe. So back here, I have done A, check, B, check, C, check. Now I'm going to do D. How does D differ from C, which is what we just did? It differs in the sense that I'm not using don't cares anymore. I am going to specify the transition to 0 at the next clock edge for each of my invalid states. Let's go ahead and do that. So I'm coming back here to my excitation table. This is the excitation table I used for the last example when I had the don't care conditions. And I know that I had the don't care conditions because of these giant X's over here. So what I'm going to do is I'm going to fill out, instead of X's, I have now specified that my next state is going to be 0. So if I should happen to be in one of those invalid states at the next clock transition, I'm going to reset back to 0. And in fact, let's take a look at the state transition diagram and see how what I just said reflects in the state transition diagram. So nothing changes here in the valid counting sequence. This is still a mod-10 counter, which means it goes from 0 all the way to 9 and then it resets. But what about the invalid states? So I've got these invalid states over here, and now I've specified, I have told you that actually they are all just going to go to 0 at the next clock edge. So that's my state transition diagram. I don't have to do that invalid state table that I have been doing up until now. So let's go back to the excitation table over here. So what control inputs do I need? So I hope you know by now how to fill out an excitation table. So I'm going to look again, flip-flop by flip-flop, and I'm going to fill out my control inputs. So I've made you a little table with the Boolean expressions for the control inputs for the 3 fully synchronous mod-10 up counters that we did, because I think it's instructive to compare them. So over here on the top row, I've got the flip-flop type. And here I've got, what do I do with the invalid next states? And for these two, it's don't care. And for this one, we said it was 0, 0, 0, 0. So looking, I can see that for the D flip-flop, I have maybe somewhat more complex expressions, but I have way fewer of them. I only have 4, as compared to the JK flip-flops where I have 8 expressions. However, in the case of the don't care condition, I can see that actually these are really, really simplified, and I could get away with, let's see, one 3-input AND gate, one 2-input AND gate, and another 2-input AND gate. So really, that's not a lot of logic gates. And over here, especially comparing it with the other JK counter, I can see that I still have double the number of logic expressions, and my logic expressions are slightly more complex. So, for example, I have way more OR gates. I don't have any OR gates in this case, but I have quite a few here. So this is a comparison of the 3 fully synchronous mod 10 up counters that we did.